Hi everyone, welcome to the presentation of our paper on training robust PDF malware classifiers. My name is Yizhen, and I'm presenting this on behalf of my co-authors, Shiqi Dongdong and Suman from Columbia University. Security classifiers are used to detect malware, online fraud, Twitter spam, and all sorts of malicious activities. We can train these classifiers with almost perfect accuracy and extremely low false positive rate. However, they are very easy to evade. As an example, we can evade Gmail's PDF malware classifier using the following action. We inserted pages from a machine learning textbook to a PDF malware and uploaded the malware variant as an attachment to Gmail. While Gmail can detect the original PDF as malicious, the malware variant is classified as benign. Security classifiers should at least be robust against such trivial attacks. Let's look at what changed in the PDF malware in this attack. The portable document format can be parsed into a tree structure as shown here. For this particular malware, under the root of the tree, there are 3 subtrees. The exploit is contained in the object under the path /root/openaction/js. By inserting textbook pages into the malware, we inserted over 12,000 objects under the /root/pages subtree, and we kept the maliciousness of the PDF. For any security classifier to be practically useful, it must have robustness in addition to having high accuracy. In this case, the malware classifier should have a robustness property that it keeps the malicious prediction no matter how many benign pages are inserted into the PDF malware. As another example robustness property, the classifier should keep malicious prediction if non-functional objects are deleted from the malware. Here, the figure shows that an attacker should not be able to evade the classifier by deleting the non-functional length field of the exploit. In this paper, we take the first steps to train verifiable robustness properties for PDF malware classifiers. Why are the robustness properties useful? Our key idea is the following. Given enough resources, unbounded attackers can always evade the classifier. Therefore, we evaluate a classifier's robustness against attackers within some reasonable bound. Since classifiers learn to generalize, if we train a classifier with robustness against bounded attackers, it should generalize the robustness against unbounded attackers to some degree. Here, we would like to achieve the robustness by defining reasonably bounded attackers in our robustness properties and measure the robustness using a new metric, robust accuracy. We define robust accuracy as the following. Given the space of all samples we want to predict, the classifier is accurate on some of them. Then within the accurate samples, we evaluate how robust the classifier is, whether it predicts them in the same way within some restricted threat model. We define this set of robust and accurate samples to be the robust accuracy of the classifier. In other words, given a test set, robust accuracy measures the percentage of samples that are correctly classified against any attacker within a specified bound. For example, attackers against an image classifier can be bounded by LP norm. We define 2 types of robust accuracy. First, the estimated robust accuracy, ERA, measures robustness using known attacks. We can measure ERA against restricted attackers. We can also measure how ERA drops for a trained classifier as the bound increases for unrestricted attackers. The second metric is verified robust accuracy, VRA, which measures robustness using sound over approximation methods. These methods over approximate attacks and therefore usually provide a lower bound of the percentage of robust and accurate samples. There are many different types of sound over approximation methods to verify the robustness of neural network models. In this paper, we use the symbolic linear relaxation method. On a high level, given input bound of a data point, we derive the overestimated output bound, which tells us whether a data point is always correctly classified given the input bound. This over-approximates potential attacks and can be used to measure VRA of trained classifiers. A naturally trained classifier may not obtain high verifiable robustness. We can use verifiable training to increase the VRA of a classifier. Verifiable training is one type of robust training method. While regular training has the objective to minimize the classification errors in the training data, robust training solves a minimax problem. We first maximize the classification errors by all successful evasions in the training data. Then we minimize such errors to train robust models. There are two types of robust training methods: adversarial training and verifiable training. Adversarial training uses existing attacks to estimate the maximal errors found in the training instances. We use verifiable training in this paper. Verifiable training uses sound over approximation techniques to get an upper bound of the maximal errors for all potential evasions, which bounds even the unknown attacks, and then train the robust neural network models to achieve VRA. To obtain verifiable robustness properties with high VRAs, we need to address the following challenges. First, how can we train a single model to be robust against different attackers? Second, how do we maintain low false positive rate for the robust model? And lastly, how does verifiable robustness generalize to unrestricted attackers? For a model to be robust against different attackers, it needs to obtain VRA for multiple robustness properties, as well as regular test accuracy. This makes the underlying optimization problem harder. To address this, we use mixed training technique with combined training objective. In addition, during training, we randomly mix the batches belonging to different properties to balance the training goals. To train the properties, we propose a new distance metric to bound the attackers that reasonably mimic real attackers. Moreover, the bounds should not affect the false positive rate of the robust model. Adversarial malware examples are actually not defined with a proper bound for robust training. The requirement is to perturb original malware X and get the variant X prime subject to two constraints. First, the classifier F thinks X prime is benign, and second, an oracle can verify that X prime preserves malicious functionality. The oracle here captures that changes in the malware variant is imperceptible by the machine. To define the new distance metric, we looked at how real attacks search for evasive PDF malware variants. The attacks start from a PDF malware seed, conducts a series of building block operations while keeping the maliciousness of the PDF until it succeeds at evading the target malware classifier. The building block operations include inserting features, merging benign features to the malicious feature vector, and basic mutation operations. The attacks optimize the search process using different methods, including gradient descent, genetic evolution, and hill climbing. Inspired by this, we define our distance metric to capture the building block attack operations. And the larger distance would mean that more building block attack operations are done. We propose a subtree distance for PDF malware variants. During the evasion process, a PDF malware variant needs both the correct syntax and the correct semantic to stay functional. And we focus on the syntax part of the PDF tree. We use the subtree distance to capture the number of different subtrees under the root between malware variants. For example, on the right side, the malware variant has changed in the subtree /open action, where the length field of the exploit is deleted, but the other two subtrees are the same. In this case, the subtree distance is 1, which captures arbitrary changes in 1 out of n total subtrees under the root. The subtree distance can be extended to the number of multiple different subtrees under the root. In our experiments, we found that training only 2 building block robustness properties can maintain low false positive rate. They are the subtree insertion and deletion properties at distance 1. Subtree insertion property at distance 1 specifies that given a PDF malware, all possible manipulations to the PDF bounded by inserting in an arbitrary subtree under the root do not result in a benign prediction. The subtree deletion property at distance 1 states that given a PDF malware, all possible manipulations to the PDF bounded by deleting within an arbitrary subtree under the root do not result in a benign prediction. Both properties over-approximate potential attacks. Using the headless binary path features, we train our verifiably robust model with these 2 building block robustness properties. As shown in the right column of the table, our verifiably robust model achieved high VRAs for both subtree insertion and deletion properties, while maintaining high accuracy and low false positive rate. In comparison, one of the strongest baseline models, the monotonic classifier, can achieve high VRA for the insertion property, but not the deletion one. The monotonic classifier also sacrificed the false positive rate, increased the false positive rate to be 3 times of our model. For every 2 data points, the monotonic classifier has a non-decreasing prediction function for all the feature dimensions, which covers the Subtree insertion property but not the deletion one. Overall, our verifiably robust model is more balanced at achieving different types of VRAs and maintaining low false positive rate. Then we further evaluated the robustness of these models against unrestricted adaptive attacks. We modified the strongest unbounded black box attack, the genetic evolutionary attack, to target the properties of the robust classifiers. To target the monotonicity, we designed a new mutation operator to move exploit around to different triggers in the PDF. This effectively conducts deletion on some feature dimension, but still keeps the exploit somewhere else. To target our verifiably robust model, we modify the mutation process to spread out insertion and deletion in the different subtrees. The results show that our verifiably robust model is harder to evade. As shown in the dashed lines of the 2 figures, our model requires 3.7 times more mutations and 10 times larger L0 distance to be evaded by adaptive attackers compared to the monotonic classifier baseline. We have conducted extensive evaluations for multiple verifiably robust models against 12 baseline models using 7 different attackers. By training verifiable robustness properties, we can raise the bar against unbounded attackers. The details of the results are in our paper. Thank you for watching this presentation. We have released our source code and models on GitHub. I'll be happy to answer questions during the Q&A session.